Hello friends, today we will discuss about Fermat's little theorem. This is a very important and useful theorem in modular arithmetic. This theorem simplifies the computation of exponents in modular arithmetic. Before going into details of Fermat's little theorem, I will just describe some basic concepts which are useful in this theorem, Fermat's little theorem. There are four basic concepts which are useful in this theorem. First one is prime number. We all know that a number which is divisible by itself or 1 is known as prime number. Second is co-prime or relatively prime. Two integers are said to be co-prime or relatively prime if their greatest common divisor is 1. It is not necessary for those integers to be prime. Only the condition is the greatest common divisor between two integers is 1. Then these integers are known as co-prime or relatively prime. For example, 4, 7. The greatest common divisor of 4, 7 is 1. It means 4, 7 are co-prime or relatively prime. However, 4 is not a prime number. Third is modulus operator. The modulus operator gives us the remainder. For example, if I say 7, if I write 7 mod 2, it means 7 will be divided by 2 and the resultant remainder will be the resultant, that is equals to 1 in this particular example. Fourth one is the multiplicative property, which is very useful to understand the Fermat's little theorem. Multiplicative property states if A cross B mod C is equals to, A cross B mod C may be written as A mod C into B mod C whole mod C. For example, we have to calculate this 40 square mod 19. So first we can write 40 square mod 19 as 40 into 40 mod 19. Now with the help of multiplicative property, first 40 is A, second is B, we can write 40 mod 19 into 40 mod 19 whole mod 19. 40 mod 19 means 40 divided by 9, resultant will be the remainder and the remainder is 2. So 2 cross 2 mod 19, that is 4 mod 19, and 4 mod 19 means 4 because 4 is not divisible by 19. This is multiplicative property is useful when the exponent power is much small. But what if the exponent power is much high? For example, if we have to calculate 40 raised to the power 40. This will be impractical to solve with the help of this multiplicative property because again it will have a very large computation. So, to overcome this problem, here is the needs of Fermat's little theorem. Fermat's little theorem simplifies the computation of exponent in modular arithmetic. First, we will study the statement of Fermat's little theorem. What is the statement of Fermat's little theorem? Fermat's little theorem states if P is a prime number and N is a positive integer not divisible by P. If I say N is a positive integer not divisible by P, it means N, P are relatively prime or co-prime. So, in Fermat's little theorem, we have a prime number P and we have an integer N that is relatively prime to this number. Then N raised to the power P is equals to N mod P according to Fermat's little theorem, or N raised to the power P is congruent to 1 mod P. If I say congruent to 1 mod P, it means if I say N raised to the power P minus 1 is congruent to 1 mod P, it means N raised to the power P minus 1 mod P, N raised to the power P minus 1 mod P is equals to 1 mod P. N raised to the power P minus 1 mod P is equals to 1 mod P. For example, let's say N equals to 3, P equals to 7. First we will check that P is a prime number. Yes, 7 is a prime number. And now we will check that 3, 7 are relatively prime. Yes, 3, 7 are relatively prime. Then according to Fermat's little theorem, 3 to the power 7 minus 1 will be congruent to 1 mod 7. 3 to the power 7 minus 1 means 3 to the power 6 is congruent to 1 mod 7. 3 to the power 6 comes out to be 729 is congruent to 1 mod 7. Or for another example, let p is equals to 5, n is equals to 2. Yes, p is a prime number, n comma 2 are co-prime. Then 2 to the power p minus 1 means 2 to the power 4 will be congruent to 1 mod p, or 16 will be congruent to 1 mod p. Obviously 16 is congruent to 1 mod p because 16 mod p is equals to 1 and 1 mod p is equals to 1. Now we will prove the theorem how Fermat's theorem is true. To prove this theorem, we can take a prime number p and an integer n that is relatively prime to p, because for Fermat's theorem there are two conditions. There should be a prime number, there should be an integer that is relatively prime to this number. Now we consider the set of positive integers less than p, means the capital P set p consists of integers less than p, 1, 2 up to p minus 1. Now we multiply each element of this set p with n mod p. Here another set x will be n mod p, 2n mod p up to p minus 1. Sorry, it is p minus 1 n mod p. We find two facts about this set x. All elements of set x are non-zero because p does not divide n. We have already taken that n comma p are relatively prime. It means p does not divide m. If p does not divide m, it means there will always be some remainder when we find n mod p. So all elements of x are non-zero. They cannot be 0 because already we have taken 1 comma p minus 1 to p minus 1 is positive integer. So 0 is not included in this. Also 0 is not included in this. It means there will be all elements will be the non-zero elements. Now second is no two numbers or elements of set x are equal. Though two elements of set x cannot be equal. For example, if we take two elements of set x is equal, it means Jn is congruent to Kn mod p, means Jn mod p is equals to Kn mod p, where J and K are element from this set p, and Jn mod p and Kn mod p are the element of this set x. Now n is relatively prime to p. It means we can omit the n because p does not divide m. So if we omit the n from both sides, then j will be congruent to k mod p, or which is the contradiction, because j mod p cannot be equals to k mod p. We have taken different element less than p. For example, we can understand this with this example. Let's say we have a prime p, and if we take all positive integers less than p, then they will be 1, 2, 3, 4, 5, 6, 8. And when we take again the mod of p with these elements, 1 mod p will be 1, 2 mod p will be 2, 3 mod 3 will be 3, 4 mod p will be 4, 5 mod 7 will be 5, 6 mod 7 will be, sorry, it is 6. So it is not possible that 5 mod 7 is equals to 6 mod 7. Hence we can say that all elements of this set x are distinct elements. Now we have find out the two facts about set x. Set x have p minus 1 element. All are positive integers with no two elements equal. Set x consists of set of integers 1 to p minus 1 in some order. Because if we have a prime p and we have all the positive integers less than p, and then we take mod, then it is again repeating those elements in some order. We know with the property of modular arithmetic that if A is congruent to B mod m and C is congruent to B mod m, then AC will be equals to BD mod m. So by applying this property into the element of set x, n into 2n up to p minus 1n will be the congruent to 1, 2 up to p minus 1 mod p. So if we multiply n p minus 1 times, then it comes out to be n raised to the power p minus 1, and 1 into 2 up to p minus 1 is factorial p minus 1. Same is for right hand side, factorial p minus 1 mod p. Factorial p minus 1 may be cancelled because It is relatively prime to p. Hence, the Fermat's theorem is proved. N raised to the power p minus 1 is 1 mod p, or n raised to the power p is congruent to n mod p. N raised to the power p minus 1 is 1 mod p, or n raised to the power p is congruent to n mod p. Now we will check how Fermat's theorem is used with the help of an example. Let's say we have to calculate this 9 raised to the power 794 modulo 73. We have to calculate 9 raised to the power 794 modulo 73 by Fermat's theorem. So here n is equals to 9. This 9 is n if we use Fermat's theorem, and this 73 is p. First we will check 73 should be a prime number and n comma p should be relatively prime to each other. Yes, 73 is a prime number and 9 and 73 is not divisible by 9. It means 9 comma 73 are relatively prime to each other. Hence, the Fermat's theorem is applicable to this particular problem. So, how we will check how we apply the Fermat's theorem. Here n is equals to 9, p is equals to 73. So, according to Fermat's theorem, n raised to the power p minus 1 is congruent to 1 mod p. Now substitute the value of n and p. 9 raised to the power 73 minus 1 is congruent to 1 mod 73. It means 9 raised to the power 72 is congruent to 1 mod 73. Now, with the help of division algorithm, we will express this 794 in terms of 72. So 794 will be 11 into 72 plus 2. So now 9 raised to the power 72 into 11 will be 1 mod 73. Here first we will do 9 raised to the power 72. 9 raised to the power 72, 11 is congruent to 1 to the power 11 mod 73. 1 to the power 11 mod 73. Then 1 to the power 11 is nothing but 1. So we write here. Now this equation come here. 9 raised to the power 72. 11 is equals to 1 mod 73. Now to make it equal to 794, we multiply both sides with 9 square. Then 9 raised to the power 792 into 9 square is congruent to 9 square dot 1 mod 73. Means 9 raised to the power 794 is congruent to 81 mod 73. It means 9 raised to the power 794. 9 raised to the power 794 mod 73 9 raised to the power 794 mod 73 will be equals to 9 square, or we can say 81 mod 73. Here now this 9 raised to the power, what is 81 mod 73? 81 mod 73 is easy to calculate. It is only 8. So 9 raised to the power 794 mod 73 will be 8. Here we have seen how simple the calculation is if we are using Fermat's theorem. If Fermat's theorem is applicable to some particular problem, then it simplifies the computation of exponent and it makes the problem much easier to solve in less computation time, less complex application, and very easy to solve. So in this way Fermat's theorem is very useful if we are talking about the modular arithmetic. Thank you friends. Hope the lecture will be useful for you. See you in the other lecture. Thank you very much.